Thank you for attending today's webinar on the essentials of air sampling from strategy to solutions. The life science business of Merck KGaA in Darmstadt, Germany operates as Millipore Sigma in the United States and Canada. This slide shows my contact details. After this webinar, please feel free to contact me should you have any questions about what has been presented today. Today's agenda includes an overview of the air sampling workflow, using the workflow to develop an air sampling strategy, how to select the right air sampling devices for your application, a discussion of passive air sampling devices, and analysis of air samples. The first step in developing an air sampling strategy is understanding what the air sampling workflow looks like, from collecting the sample to the laboratory analysis. The overview of that process will be discussed. When developing the process for taking an air sample, it's important to understand that air sampling is a process used to determine which analytes or airborne contaminants are present in the environment that you are sampling. This slide shows some different environments where you might be taking an air sample: industrial hygiene in the workplace, ambient air, also for product emissions, source air, also in healthcare for anesthetic gases, for cancer screening in some applications, also in national security. So it's important to understand where you're taking the air sample, what those concentrations are in those environments, and which devices are most suitable for those environments. Why do we take air samples? We take air samples to detect, measure, and quantify contaminants as a means of ensuring compliance with applicable laws as they relate to personal exposure and environmental health. We also take air samples as a means of prevention of accidental exposures or emissions, and also as a measure in emergency response. The air sampling workflow contains 4 distinct steps. The first step is collection of the air sample, and the other steps are at the laboratory. Those steps are sample preparation, analysis after sample preparation, and results interpretation. This is a more expanded view of the air sampling workflow. The air sampling workflow starts with your purpose of air sampling and your objective. Which sample collection media or device, as they're also known, will you be using to take your air sample? Once that's determined, you will then collect the air sample. After you collect the air sample, you will package it up for shipment to the laboratory. At the laboratory, they perform what's called a workup or desorption procedure for those samples that require desorption. And then after desorption or any other preparative steps, the sample then goes into an instrument for analysis. Most often, the analysis is by chromatography or spectroscopy. In this type of sampling scenario, you do not get the results back immediately. They take several days. Oftentimes, from shipping then to analysis, it can be a week or more. Some laboratories do have expedited testing if you request it. And then the laboratory will form a report from the analysis, evaluate the data, and send it to you so you can make your informed decisions. When selecting the right air sampling devices, your laboratory, your environmental health and safety officer might ask that you refer to regulatory agencies in your country, in your locality, and refer to their method databases to find a method to collect the air sample. If there are no methods available in your region, it is common to refer to methods outside your country that have been validated. Now that you have an understanding of what the air sampling workflow looks like from sample collection through analysis, I'm going to discuss how to develop a strategy based on that information. So where do you begin when you're developing your air sampling strategy? The first place is to contact your laboratory partner for advice. Explain the situation, what you suspect is the contaminant, and then they can assist you with some guided questions on developing a solution to collect air samples. If you do not have a laboratory that you work with, there are web searches that you can do that can help you find a laboratory to help you. If you know the source of contamination, another place to start is consulting the SDS. And this is particularly important if you know what the chemical inventory is in that area. You can then follow the SDSs, look in Section 8, which is especially helpful for exposure control, which also has exposure limits and personal protective equipment. However, if you don't know the chemical contaminants, if you're starting from scratch, and particularly if it's in an industrial work environment, still go to those facility documents and look at the chemical inventory in that area. Also look for the chemical inventory in adjacent areas. Oftentimes, facilities do share air handling. There could be, an air intake from the outside that could be causing the problem. So it's very important that you not only survey the area if you don't know, also adjacent areas and the outside, particularly where air intake comes into the building. Also interview the workers. They might be able to say, oh, well, something was a little different, but I didn't think anything of it. Or, maybe they didn't think they could say anything because nothing changed. So it's very important to interview the workers and people in the vicinity. Also in that area, have any mechanical processes changed? Have there been any changes to the maintenance protocol? Have there been any improvements or upgrades made? Are there any new processes in the area? And assessing those processes and the operating procedures in the area will also help on giving some idea as to where the contamination source is coming from. So those are important questions to ask when you're beginning your journey, and some ideas on where to look and what to do. And continuing on that, you have consulted and you are consulting with your laboratory partner or your environmental health and safety officer, industrial hygienist, or perhaps you contracted a service to help you on this journey. So the next part is the sample collection. You have an idea, you know where you want to look, but what devices am I going to use? How am I going to do it? So most importantly is to first recognize the recommendations that the laboratory has provided to you. Also, you're attending this webinar today, but perhaps you've attended other webinars or read something in a journal, and you have seen information on new devices and new techniques, and you thought maybe that it might apply or be useful in your application. Contact the laboratory and ask them if they've heard of it, and two, if they can test it. That can also be something in your pocket to help you determine the right device for your application. Also, the regulatory agency published methods. I put a slide up a few slides ago that listed some common regulatory agencies and their methodology. Please also check there for the sampling device that they recommend. And in selecting the sampling device, we saw a slide that had many different environments where air samples are taken. And devices are often made with concentration in mind. So please, when you're communicating to your laboratory or resource to help you choose a sampler, that you communicate and discuss the concentration range, what types of limits of detection that you're looking for. Is the device sensitive for the analytes you're looking for? Are there any interferences? And also, which type of sampler do you prefer to use? Active samplers or passive samplers? Those will be discussed. So in developing a strategy, these are some key questions to ask yourself and keep in mind as you are trying to pinpoint the source, and if you know the source, some questions to ask when you are determining what type of sampling device to choose. And now selecting the right sampling device for your application. When we talk of air sampling devices, they usually fall into many categories. Shown on this slide are 3 different air sampling techniques. Active sampling, which requires an air sampling pump that draws the air into the sample collection device. There are passive sampling devices that draw the air into the passive device through molecular diffusion. And there's also whole air sampling, which is another type of active sampling, and it's used more commonly in environmental applications, and they will not be further discussed in this webinar. As you can see, there are several different devices shown for active and passive sampling. So how do you choose? When selecting an air sampling device, there are some additional points to consider. The first is, does the capacity of the device meet the needs of your application? For example, in the workplace, capacity as determined by US OSHA means the device must be able to measure at 2 times the personal exposure limit. Is the device you're selecting have that capacity that you need? Capacity can be affected by environmental conditions. Humidity, temperature, and light all play a role in how the device collects contaminants in the air. For example, devices that have sorbents, say like silica gel on the inside, that are sampling in humid environments, the water can displace the analyte and take up capacity inside the sorbent tube. So in that instance, choosing a silica gel tube in a high humidity environment would not be the recommended sorbent to select when taking your air sample. And what does your sampling terrain look like? The example of relative humidity and water vapor affecting the collection of contaminants would require another device in the sampling train. Often used would be an ozone scrubber, and that can help collect some of the water vapor before it goes into the sorbent tube. And what happens when the capacity of the sorbent tube is taken up by water vapor or another competing analyte is that there can be what's called analyte breakthrough. And that's when the analyte collected exceeds the capacity of the adsorbent on the inside of the tube. And this example here was from an OSHA study on diacetyl in high humidity. What happened was, in high humidity, the water vapor displaced the analyte and forced the analyte into the backup bed of the tube. So this is an illustration of what analyte breakthrough looks like. When determining what sampling technique that you want to use, active or sampling, this slide is a summary of active and passive air sampling techniques. Just reiterating that the active air sampling device requires a pump to collect air samples, and that it collects these air samples at a predetermined flow rate and volume into the adsorbent bed, and that the pump's flow rate must be calibrated and verified before and after sampling. Passive air sampling, there are 2 types of devices, axial or 2D, as shown in the left, that looks disc-like, and radial devices as shown by the device on the right. With passive sampling, no pump is required because the natural process of molecular diffusion forces the contaminants to diffuse onto the adsorbent bed, and that each analyte has its own diffusion rate into the adsorbent bed. And it is important to make sure that you select your device that has validated uptake rates versus experimental uptake rates. They give you the best results when choosing a passive sampling device. And the manufacturers of those devices, when they publish their sampling rates, will have it listed whether it was experimental or calculated. And for passive sampling devices, whether axial or radial, a minimum airflow of 5 meters per second is required. When trying to decide on which air sampling technique that you would use for your application, it's important to understand the advantages and disadvantages. For active sampling, there are a wide variety of sampling devices available, and these devices are tied to validated regulatory agency methods. And in these methods, there are listed flexible flow rate ranges to accommodate your applications and sampling needs. And with active sampling, you can sample more than one tube or one product at a time with a pump accessory. So if you are considering doing more sampling, you would be able to do more than one at the same time. And if you don't own a pump, you can also work with your laboratories to perhaps rent a pump or have that somehow included in your cost of analysis. There are also distributors that do offer pump rentals as well. And if you are doing your sampling and trying to decide on which product to use, there are products called thermal desorption tubes, which are used for volatile organic compounds, and those tubes are reusable. So that's something to consider as well that can help lessen the cost. The disadvantages of active sampling are mainly due to equipment needs. If you own pumps or have to manage pumps in your facility, you know that they can be labor intensive to calibrate, pre and post. They can be expensive to certify and maintain. Also, during operation, pumps can fail. It's a piece of electronic equipment, and when it fails, you can lose your sample, which is also another added cost. And then you would have to schedule another sampling event. So please take those into consideration. And most of all, workers really don't like to wear pumps and tubings and those types of things, particularly if it can impede how they perform their jobs. So those are just some things to consider when deciding on whether to choose active sampling as one of your sampling techniques. Before you take an air sample, the sampling train must be calibrated before sampling and then after sampling. And it's important to calibrate the flow rate with the air sampling device and the tubing connected to the pump to ensure that the flow rate is being delivered accurately, and that you know that the sample volume you're collecting is also accurate. So it's important that the flow rate remains constant during sampling, that your equipment is reliable during sampling, and that you can confidently state that you have collected the air volume as recommended in the method. And then after sampling, this also needs to be done again to ensure that the flow rate and the volume collected was maintained, or at least within the deviation required for the device. Now I'm going to discuss some active sampling media for specific contaminants. The first group I'm going to talk about are organic vapors. And how you would know these is they are vapors that arise from petroleum-based liquids that evaporate quickly. And there are many contaminants in this group. This group was previously analyzed by OSHA Method 7, which had over 70 contaminants listed with varying instructions. What OSHA has now done is updated the methods into new sampling groups to provide more guidance and instructions to the laboratory. So if you're not familiar with this new update that happened in 2021, you can go to OSHA's website and read more about it. How OSHA has grouped these organic vapors is into three groups. The first group is OVSG1, and it's for contaminants that are desorbed with carbon disulfide. And these are most commonly sampled with coconut charcoal tubes, and they look like what is shown in the picture at the bottom of this slide. Another group now is organic vapors for alcohols, and they are sampled on synthetic carbons. In this case, a carbon molecular sieve. And method group 3 for organic vapors, OSHA has modified has moved away from their former methods 42 and 47 for isocyanates to now method 5002. Another way to look at organic vapors is typically the term used in industrial hygiene, whereas the term volatile organic compounds is more commonly used in environmental applications. So while they are pretty much the same compounds, there are some differences in the sampling techniques. So when you are sampling for organic vapors or volatile organic compounds, you can choose to use two different device types. In the previous slide, you saw an example of a glass sorbent tube with coconut shell charcoal. Thermal desorption tubes are different in that they're not desorbed by solvents. And what's nice about them is they have detection limits that are up to 1,000 times greater than organic vapor sampling tubes. And that's because there's no solvent desorption. And because of this, they can monitor at ppb and ppt levels. They're desorbed by heat. There's no solvent artifacts or interferences. They have high desorption efficiencies and greater reproducibility, and they're less affected by environmental conditions. And at the laboratory, they're not amenable to sample preparation errors because they go from taking a sample to the lab right to the instrument. There's no separate preparation step. It reduces exposure limit levels, particularly in the laboratory, because analysis doesn't require carbon disulfide. And particularly in some countries around the world, there are restrictions to the use of carbon disulfide. So if you choose, say, organic vapor sampler over a thermal desorption tube, it might be more costly in that the cost to have a license or permission to use carbon disulfide could be very expensive. And these thermal desorption tubes are also cost effective because they can be reused 50 to 100 times, because after the sample is removed off the device, they are reconditioned and ready to take on the next sample. The next sampling group I'm going to discuss are called the carbonyls, and aldehydes and ketones fall into this group. So what is a carbonyl? A carbonyl is a functional group that contains a carbon double bonded to oxygen. And of these contaminants, aldehydes and ketones, the aldehydes are typically more reactive than ketones due to the following factors. Aldehydes are less hindered than ketones because the hydrogen atom is smaller than any other organic group. And the carbonyl carbon in the aldehydes generally has more partial positive charge than the ketones due to the electron donating nature of the alkyl group. Aldehydes only have one electron donor group, while the ketones have two. Therefore, for the ketones, derivatization is not required because it is a more stable type compound. There are many different devices available for sampling of carbonyls, particularly aldehydes and acetone in air, using devices that contain a silica gel or fluorosil adsorbent that is coated with 2,4-dinitrophenylhydrazine or 2,4-DNPH reagent. And the tube styles vary, as well as a selection of devices available by carbonyl capacity. Most of the methods that are referenced are based on the EPA method TO11A, NIOSH 2016, and there are others, and the typical carbonyl capacity is less than 75 micrograms. However, other devices are available for greater carbonyl capacity, particularly if your environment is expected to have a higher concentration. And for these types of devices, there typically is not a backup bed, with the exception of the Orvo 55 and 558 style, which are the industrial hygiene type devices that have the backup bed. If the contaminant group you're sampling for are isocyanates, I'm going to share some information on the different sampling devices available for those compounds. For those of you who do not know what isocyanates are, they are used in many of the common products that we use in everyday life, such as the painting on our automobiles. They're also in rigid and also in spray foam insulation and in components of our furniture. And in the workplace, they're the leading cause of occupational asthma, and some of the compounds are suspected carcinogens, as well as, they have other health effects that are detrimental, particularly to the respiratory region of the body. When we're talking about isocyanates, the most commonly used isocyanates are called diisocyanates, and they contain two isocyanate groups, at least in their structure. And the most commonly sampled diisocyanates are known as MDI, TDI, and HDI, with also IPDI being another commonly sampled diisocyanate. And then there are polyisocyanates, and they're derived from diisocyanates and contain several isocyanate groups. Polyisocyanates are larger, much larger than diisocyanates. And the most commonly occurring polyisocyanates are known as HDI biuret and HDI isocyanurate. So what type of devices are used for sampling isocyanates? And you see three different device types below. On the left is a new and innovative device called the Asset Easy4 Dry Samplers, and they'll be discussed later. There are two devices available. One is for sampling the entire range of diisocyanates and polyisocyanates, and the yellow device is for sampling the higher volatility isocyanates like methyl isocyanates and isocyanic acid. And then the device in the middle are the cassette type samplers, which you might have been familiar with from OSHA methods 4247, which has now been changed to the OSHA Vapor Sampling Group 3 or method 5002. And this would also include a sampling type that you might have heard of called IsoCheck. And then there's another device called Impinger with reagent solution, and it's a glass vial with a special head on it that sometimes has a particle cassette connected to it that uses a liquid reagent inside to collect and quickly derivatize the isocyanate compounds. The two most common devices for sampling isocyanates in the air are the 37 millimeter cassette types and the Asset EZ4 sampler shown on the right. Both devices contain glass fiber filters that are coated with a reagent that derivatizes the isocyanate into a compound that can be measured on an analytical instrument. For the 37 millimeter cassette, it has a flat type design, and in that design, only the isocyanate particles that land on the filter and have contact with the reagent derivatize. Those that pile on top above it, they do not derivatize, and therefore by not derivatizing, they cannot be measured. And that means that you would have a low recovery in this device and underestimate exposure. And the impacts of that is, a worker who is working around these isocyanates, and if you're sampling with this type of device, it might not tell you the true story about how much exposure they are encountering with isocyanates. The asset sampling device on the right-hand side is coated with dibutylamine, and what dibutylamine does is it derivatizes the isocyanates into a stable urea derivative. And the design of the denaturing filter, when the isocyanates are sampled and they travel through the denuter and the filter, there is a high concentration of dibutylamine and it completely derivatizes all the isocyanate vapors and particles that enter the device. So with the asset sampler, it has the capability of derivatizing everything that is in the device. And that gives the industrial hygienist confidence that they are providing their workers with the best measure of their safety. And you see here that the isocyanates, as they travel through the denuter to the filter, that they all completely derivatize. In the previous slide, you were shown how isocyanates behave on a traditional 37 millimeter coated filter device versus the Asset EZ4 sampler, which is a denuter and filtered device. In the Asset EZ4 samplers, we have two available. One is called the Asset EZ4 NCO sampler, and the other is known as the EZ4 ICA sampler. They both contain dibutylamine as a derivative, but at different ratios. The EZ4 sampler you would select for sampling the wide range of isocyanate, diisocyanate monomers and oligomers. And the ICA sampler you would select for the higher volatile isocyanates like isocyanic acid, methyl isocyanate, phenyl isocyanate, and the NCO would do the others. There is a wide range of flow rate to select from between the two samplers. The asset sampler, the NCO sampler, can sample for up to 12 hours because it has a high capacity in one device, and the ICA sampler for 4 hours. So compared to the traditional 37 millimeter devices or the old impingers with reagents, they are limited to sampling for 15 minutes. And 15 minutes doesn't really give you a whole picture of the work shift. The worker can keep working while wearing this without much issue. And storage, particularly for both devices, for the Asset NCO sampler, storage is ambient before and after sampling. They don't have to be refrigerated. And when you're sampling for MDI, which is found in a lot of foams, the current 37 millimeter devices require something called field desorption, where you literally have to take the filter cassette off the worker, remove the filter, derivatize it in a solution that is hazardous to ship. And there could be a lot of sample loss. There could be issues with using 37 millimeter cassettes for that technique. For the ICA sampler, the recommended sampling, again, is up to 4 hours. These do require refrigeration before sampling, but can be held at ambient after sampling. There will be no change to the compounds after sampling. And then stability for the NCO sampler, the stability is 4 weeks after sampling, and the ICA sampler is 2 weeks. So again, that gives the industrial hygienist, the EHS professional time to deal with these without having to deal with any post operations or shipping of hazardous chemicals. And this slide is shown what the analytical chemist would see when doing the analysis of the asset sampler. This is of our isocyanate standard. And what's really nice about this sampler is it's completely supported by certified reference materials and can detect aliphatic monomers, aromatic monomers, HDI adducts, polymeric MDI, IPDI, and its adducts. So it's important that when selecting the device and you in your product that contains isocyanates has any one of those compounds, that you have a sampler that can collect and measure them. And this is the only device that has that full range. It has greater flexibility and can be more cost effective to use because you don't need to use as many samplers. And these devices are much more sensitive, just giving you much better data to base your decisions. The next topic of discussion is the passive air sampling technique with focus on radial air sampling devices. The passive air sampling technique, or diffusive air sampling as it's also called, differs from active sampling in that no pump is required. It requires a minimum airflow of 5 meters per second, and it works in that the contaminated air passes into the adsorbent media in the device via molecular diffusion, and that diffusion into the device is known as the mass uptake rate or sampling rate, and that's determined by the geometry of the device. And then after sampling, passive sampling devices are then measured in the laboratory the same as active sampling. The only thing that is different is how you collect the air sample. With passive sampling, there are advantages and disadvantages. And advantages apply more so to radial type sampling in that they can sample from 15 minutes to 8 hours in the workplace, 24-hour risk assessment, and up to 3 weeks outdoors in ambient environments. Also, radial samplers' uptake rate is 2 to 3 times faster than badge type samplers and more closely correlate to active sampling flow rates. They have an attractive cost per sample. It reduces labor in the sampling process. They're convenient and easy to use because workers don't mind wearing them. They don't make any noise. The components are reusable and not much training is required. There are disadvantages to using passive sampling in that regardless if the device is axial or radial, the sampling rates are fixed by the geometry of the sampler. Badge type samplers do offer low uptake rates and are prone to back diffusion, and they often don't have the capacity to sample for full shift. However, they're great for routine monitoring where your process is under control and workers wear a badge for that extra security. So definitely the badge style passive samplers do have a place in the market for routine monitoring in controlled conditions. But when you're looking to do investigation of more significance, then it's recommended to use a radial device that has higher capacity and greater sensitivity for sampling. And a disadvantage, as previously mentioned, is that a minimum airflow is required for the molecular diffusion to occur. On this slide, it's showing the differences between an axial or 2D type sampler versus a radial sampling device. And you can see on the left-hand side some devices you might have used or seen before. And the difference is that with an axial sampler, the desorbing surface and adsorbing surface are minimal compared to a radial device. And the sampling rate of a contaminant, and in this case, looking at benzene, on the axial sampler or the badge type, the sampling or uptake rate is only 8 mLs per minute. And these are rates published by the designers of the axial sampling devices. Radial passive samplers, and in this case, Radiello, shown on the right, the sampling rate for benzene is 80 mils a minute, and that is more closely tied to an active sampling rate. So you could see there is differentiation for this one compound, as well as you will see this advantage for radial sampling in others. So when you're making a choice whether to use a badge or radial style, you can check the sampling rates and what your laboratory is using, and if you would like to use a radial sampler instead of an axial sampler, let your laboratory know. Now, looking at the two different types of radial passive sampling devices, Radiello has very high sampling rates and is amenable to also shorter sampling times if needed. Sampling rates are determined experimentally and not calculated, therefore they're very accurate. And the diffusive bodies are reusable and they're eco-friendly. It's a more sustainable option than other types of devices. They also have low detection limits and the high uptake rate, which again lends to that high capacity. So you could sample with Radiello from 15 minutes to 30 days, depending on the application. And also you could sample from 1 ppb to 1,000 ppm. There are different sampler types available. There's solvent desorption and thermal desorption types. And only the cartridges for solvent desorption need to be replaced, and the TD cartridges are reusable. There is another type of radial device on the market known as DSD sampling devices. They are ready to use right out of the packaging. There is no assembly other than removing from the storage packaging and fixating a way to hang or wear the device onto it. It's streamlined. It delivers fast sampling rates 2 to 3 times faster than badge type samplers. These were designed for sampling for 24 hours, originally developed in Japan for sick cow syndrome sampling. Select devices can sample for 7 days or longer, and they are versatile for use in indoor, air, ambient, and personal sampling. The DSD DNPH is available globally, and it's also validated using OSHA method 1007 for formaldehyde. Other devices are available but might not be available in your region. When selecting Radiello as your passive sampling device for use in your application, it is important to know that there are a wide range of cartridges available for sampling the most highly requested sampling groups as an active sampling. There are cartridges available for the carbonyls, the aldehydes, VOCs or organic vapors, hydrogen sulfide, ammonia, 1,3-butadiene, ozone, and others. And there are also a selection of diffusive bodies available that are required for sampling, and the diffusive bodies are what controls the geometry or the molecular diffusion of the contaminants into the adsorbent cartridges. We also have accessories for use with Radiello, triangular support plates, and other options to help you have what you need to sample in your application. If you are not familiar with Radiello but would like to get started, there are starter kits available for select contaminant groups. We have starter kits available for the VOCs and VTECs, hydrogen sulfide, and 1,3-butadiene. The next process that will be discussed is the analysis of air samples, which occurs after the air samples have been taken, whether active or passive. The devices go through this analysis workflow. So what happens at the laboratory when they receive your samples? They receive your samples with your paperwork that has your sample volume, any flow rate information, the location, weather conditions, and they take that information and they check in your products, and then your products are then entered into their workflow, which determines where they go to in their laboratory process. So for products that require solvent desorption, there is a sample preparation step that needs to occur before they can move on to analysis. For products like thermal desorption tubes that do not require a sample preparation step, they still have all the same check-in criteria. However, they can go to analysis more quickly. And then after sample preparation, the analysis step takes place, and then the results are generated. So that's the workflow in a nutshell. And the previous slide was a more simple version of the laboratory workflow. This is a more expanded version of the workflow. Once the air sampling device reaches the laboratory along with the sampling information, which includes the sample location, time, and volume, the air sampling device, if it requires solvent desorption, goes through the solvent desorption step, and it's prepped for analysis in the instrument. Any sample that's desorbed with carbonate sulfide and methanol will typically go through a GC analysis with any number of detectors that is specified in the method. Acetonitrile, anything desorbed with acetonitrile is analyzed by HPLC UV. And toluene is used in the sample preparation of the asset samplers, and that is analyzed by HPLC MSMS. And other devices fall in the range of ICP, ion chromatography, and spectroscopy. Another type of sampling device known as thermal desorption, those tubes do not have a sample preparation step. And with the sampling criteria that came with the tube, the laboratory goes from receipt of the sample, checking in the sample, and then staging it for analysis on a GCTD instrument. In order for the laboratory to deliver you the best results that you can have confidence in, they need to maintain a wide range of products in their workflow, from the solvents they use and the purity and quality that they use, their standards and reference materials, HPLC columns and GC columns that are designed for the application and the contaminant groups that you are looking for. They also need to have the accessories and the fittings to upkeep the equipment. They need glassware. They also have to perform proficiency testing for some methods to ensure that they are delivering the best results. So when you do contract a laboratory, it's more than just receiving the samples and putting them on the instrument. There is a range of products in the workflow that your laboratory has top of mind whenever they are doing your analysis. And then in summary, this webinar started with the overview of the air sampling workflow and discussion of the different air sampling techniques to help you make decisions on selecting the right air sampling devices for your applications. It provided you with information on where to begin and what questions to ask, and points to consider when forming your air sampling strategy. The blue boxes are those same points revisited here. And the next question that you may ask yourself is, after you have developed your strategy and done your air sampling plan, would there be a need to continue to monitor the area or the worker after taking the air samples? Was the issue resolved if there was a change or a problem? Or do you feel it would be in your best practice interest to add this to your current environmental health and safety plan? I hope that you find that these are useful to you as you go through your strategy planning. And here are my contact details again. If you have any questions or would like more information, please reach out to me and I'd be glad to answer your questions. Thank you for your time and your attention. And I hope you found this information helpful to you as you develop your air sampling strategies.